I could have evolved very differently in different universes. Scottish, Jim? Quantum mechanics is 100 years old. It's the most powerful, successful, and beautiful theory in all of science. But we still don't understand what it means. Now, I'm a quantum physicist, so of course I'll say this, but there's good reasons to think that quantum mechanics is the most powerful and important theory in all of science. In fact, it's not even just a theory. Quantum mechanics is a framework for describing the world of atoms and below. So as such, quantum mechanics underpins so much of physics and chemistry. And in fact, quantum mechanics is behind our modern world. Pretty much all of electronics is based on our understanding of the quantum world. So quantum mechanics has given us the laser, the diode, the transistor, the integrated circuit, computers, smartphones, MRI scanners, the list goes on. Without quantum mechanics, our world would be very different. And yet, at its heart, and we've struggled with this for exactly a century now, quantum mechanics does seem mysterious. Not the mathematics, we understand the mathematics, but what it's telling us about reality, the nature of reality, is still something that puzzles us and frustrates us.
The trouble is, quantum mechanics describes a world that's at odds with the one we experience. Unlike everyday objects, subatomic particles can exist in multiple states at once. And they seem connected in ways that defy space and time, while the very act of observing something changes its nature and behavior.
So why is quantum mechanics so strange? Well, to explain this, let's go back to the 19th century, when it was thought that most of physics was fully understood, and in particular, the nature of light behaving like a wave. So physicists like James Clerk Maxwell and others, Oliver Heaviside, had developed a new theory of light. And in particular, Maxwell came up with what's called the wave equation. So here, the symbol E stands for the electric field. This C is the speed of light. And there's an equivalent wave equation like this for magnetic fields, because basically electromagnetic theory tells us that light is a wave, but it's oscillating electric and magnetic fields traveling through space.
The wave equation for light has the same mathematical structure as those for sound or a vibrating string. That's because it captures the same fundamental idea. A disturbance propagating through space, carrying energy.
And it was so beautiful, so accurate, that it described all sorts of optical phenomena. And it even led to inventions like the radio. So everyone was happy.
We'll see later why this paved the way to quantum madness. But first, let's quickly step through the evidence that light is a wave, starting with polarization. Ordinary light, like sunlight, is a jumble of waves all oscillating back and forth at different angles to each other. But it's possible to reduce it to what's called polarized light. This means all the waves oscillate at a single specific angle, say perfectly vertical.
So this laser pointer produces red light that is already polarized. So if I can clamp it in here so that it stays on and shine the light on that wall. Now, the fact that it's polarized means that light is oscillating only in one direction. If I have that light pass through a glass filter, which only allows light through it in one direction, then certainly if the filter and the light are aligned, all the light gets through. But as I rotate the filter around all the way around to 90 degrees, you can see the light almost disappears. It's being blocked. Now, the wave theory of light describes this idea of polarization beautifully.
A second and compelling reason for thinking light is a wave is that, like all waves, it demonstrates interference. These are distinctive patterns that appear when waves overlap. This happens because if they're in step, they reinforce each other. If they're out of step, they cancel each other out.
To see interference in action, I've got a laser pointer, which I want to clamp to project on the wall. Now, what I've done here that's different is I've placed a hair vertically down, cutting the path of the beam in two. Don't ask whether I had to get someone else to give me a hair. What it does, of course, is split the beam into two. So two waves are now traveling and then coming together on the other side of the hair and interfering with each other. And what that gives rise to are these series of light and dark lines horizontally. So where it's bright, that's where two wave crests come together to amplify. Where it's dark is where the crest of one wave comes together with the trough of another, and they cancel each other out, so the amplitude goes to zero.
Another beautiful example of light waves interfering is the stunning colours you see on soap bubbles. Bubbles have thin skins, thousands of times thinner than a hair. Some light bounces off the outer surface, some off the inner surface. The different colours of light have different wavelengths, red the longest, blue and violet the shortest. The thickness of the bubble's skin determines the colour we see. At certain thicknesses, the two red rays will be out of step and cancel out, leaving hues of blue and green. As the water in the film slowly drains downward under gravity, the thickness constantly changes, which is why the colours swirl and shift in those beautiful patterns.
So this is another example of light behaving like a wave. Nothing seemed to be in doubt. Everyone was happy with the wave nature of light until the turn of the 20th century, when everything came crashing down.
In the first decades of the 20th century, three foundational principles in classical physics were shaken to their core: determinism, objective reality, and locality. The whole thing began with an innocent question. What's the relationship between temperature and colour? Take the filament of a light bulb. Like most things, it glows orangey red and then gets whiter as it gets hotter. But why? Investigating this question was Max Planck, who had no idea of the Pandora's box he was about to open. Planck and his colleagues built this, a black body radiator. It's a special tube that enables precise measurements of the color or frequency of the light produced at different temperatures. 10 years ago, when filming for one of my BBC documentaries, I visited the National Metrology Institute in Berlin, where they were doing a modern, more accurate version of Planck's experiment, which really shows how color changes with temperature.
The temperature inside here is 841 degrees centigrade. I can feel the heat coming off, and it's glowing with a lovely orangey red color. The temperature inside here is about 2000 degrees centigrade. And it's glowing with a much brighter, whiter colored light.
Although the light is whiter, it's red-white. There's very little blue. Why is blue so much harder to make than red? And further up the spectrum, beyond blue, the so-called ultraviolet is hardly produced at all. Even when we look at things as hot as the sun.
even the sun, at a temperature of 5,500 degrees centigrade, produces mostly white visible light and makes remarkably little ultraviolet light given how hot it is. Why is this? Why is ultraviolet light so hard to make? This remarkable failure of common sense so perplexed scientists of the late 19th century that they gave it a very dramatic name. They called it the ultraviolet catastrophe.
This curve of the electromagnetic energy emitted by the sun shows the catastrophe. Its energy peaks in the blue-green region of the spectrum. Very little long wavelength infrared light and very little short wavelength ultraviolet are made. Wave theories could explain the lack of long wavelengths, but not that of the short ones. But then, in what Planck later called an act of desperation, he cobbled together an equation to fit this curve. And although Planck didn't really grasp it at the time, it was the first sign that light doesn't always act like a continuous wave. It also acts like a stream of particles. But then came another experiment and another blow to the wave theory of light. The experiment was about how light affects electricity.
To understand what was happening, scientists used this. It's called a gold leaf electroscope. Now, first of all, I have to charge it up. What I'm doing is adding an excess of electrons that are pushing the two gold leaves apart. Now, first I take red light and shine it on the metal surface, and nothing happens. Even if I increase the brightness of the light, still the gold leaves aren't affected.
Now I'll try this special blue light, rich in ultraviolet.
Immediately, the gold leaves collapse.
And let's be really clear about what we're seeing here. Even really weak UV light seems to be able to knock out electrons from the gold leaves, so they no longer repel each other. But no matter how strong a red light we use, nothing happens. Their efficacy seems to relate to the color, not intensity. This was called the photoelectric effect, and there was nothing in the wave theory of light which could explain it. A new way of thinking was needed, and that came, of course, from Albert Einstein. In the first of his papers in the so-called Annus Mirabilis of 1905, Einstein emphatically declared that the particle nature of light was the only explanation for the ultraviolet catastrophe, black-body radiation, and the photoelectric effect. The energy in a light ray, he wrote, consists of a finite number of energy quanta, localized in space, which move without being divided, and which can be absorbed or emitted only as a whole. So how do light quanta, or photons as they came to be known, explain the photoelectric effect? Well, say you want to knock over these cans. Then think of a red light photon as a light ping pong ball. Throwing many of them doesn't dislodge a single can. Think of a blue light photon as a heavy golf ball. Just a few will do the trick. Similarly, the lower frequency red light photons each carry little energy and can't dislodge electrons. Higher frequency ultraviolet photons each carry more energy and knock them out with ease.
The equation that Max Planck came up with to explain black-body radiation, and which Einstein used a few years later to explain the photoelectric effect, is very simple. It's written like this: energy equals h times frequency. H is Planck's constant. What it tells us is that the energy of light is proportional to its frequency. But it describes light as being composed of particles, photons. Now, photons describe and explain the photoelectric effect and blackbody radiation. But how do they do when we try to explain the wave phenomena that I explained earlier? For example, with the polarizer. Now, remember, when the polarizer is parallel with the light beam, it lets all the light through. 90 degrees, it stops almost all the light. What if the polarizer was at 45 degrees? Now, half the light would get through and half will be stopped. But if light is made of photons, how does this work? All the photons should be identical to each other. They all have the same phase because this is laser light, and they all have the same frequency, the same color. So what is it that tells any particular photon whether it's allowed through the polarizer or not? Then with the interference pattern experiment, presumably every photon has to go on one side of that hair or the other. But then if that is true, after many photons have gone through, we should see just 2 bright spots corresponding to each side of the hair. And yet we see these multiple light and dark fringes. It seems that light as particles can explain some phenomena, but we need to think of light as waves to explain other phenomena. This schizophrenic nature of light, this wave-particle duality, is one of the first big mysteries of quantum mechanics. Within a few years of Planck and Einstein's work, it was discovered that it's not just light that behaves like this. Matter particles too, electrons, can also behave like waves.
Wave-particle duality is the gateway to all the strange things quantum mechanics says about reality. To see how weird it gets, you need to study individual particles, like photons. But you need sophisticated equipment to do that, which is why we're visiting the physics department at Glasgow University. This equipment is designed so 1 photon at a time travels through this red-coated fiber optic cable and into this box. Inside it is a card with 2 slits. Famously, if normal rays of light were to go through it, we'd see wave-like interference patterns, like this. But this camera will show what individual photons will do. Common sense suggests that the photons will either go through one slit or another, building up 2 bright patches on the screen. But what do we actually see?
And initially you would see something which looks kind of random, but over time, we will start seeing these dark and bright patches on the camera sensor. And those are basically the interference pattern we expect to see with waves. But here we see that with single photons.
The photons appear to arrive at random. Here's one, and then another, and another, but wait long enough and distinctive interference fringes, the signature of waves, appear. But here's the first baffling thing about this. Every photon is identical and is subject to identical initial conditions and forces, but no 2 behave identically. This is completely different in classical physics. Here, identical objects, subject to identical initial conditions and forces, have identical outcomes. In effect, wave-particle duality means that we can't say with certainty what path an individual photon follows. As a consequence, we can't predict accurately what it will do. And this uncertainty represents the first of the 3 blows to the foundations of classical physics.
The first sacred idea that quantum mechanics seem to be forcing us to abandon is called determinism. We live in a Newtonian clockwork universe, or so we believed, that effect follows cause, that we should be able to predict the future if we had enough information about the present. Think of the flip of a coin. Sure, we can't predict if it's going to land heads or tails, but if we knew precisely how much force we applied to it, things like air pressure and so on, we'd be able to work out exactly how many times it spins before it lands, and so predict whether it's going to land heads or tails.
But in the two-slit experiment, we have no way of predicting with certainty where an individual photon will end up.
This is called indeterminism, and it was one of the central features of quantum mechanics as described by the founding fathers. It tells us that our world is not deterministic. It's ruled by probability and chance.
But it gets worse. And yes, there's another hammer blow coming. To see how, let's revisit the single photons going through the double slit.
Now, this is what was really baffling to the early quantum pioneers. Certainly it baffled Einstein. Each photon is arriving separately through the two slits, hitting the screen at a particular spot. It's unpredictable where a photon's going to land. It's indeterministic. And yet, after many, many photons pass through the slits and land on the screen, they build up a deterministic interference pattern. It's as though each photon by itself is somehow contributing to the overall wave-like behavior.
So quantum behavior isn't completely random. There's enough of a pattern to suggest that though you can't predict with certainty what will happen, perhaps there's a mathematical formula for calculating the probability of what will happen. This was the mindset of many of the founders of quantum mechanics, though they focused on electrons rather than photons. It's worth getting a handle on this approach because they succeeded, but at a cost. On the one hand, it worked, but on the other, as we'll see, it shattered our notions of reality. So let's begin by looking for clues in well-understood classical physics.
This animation shows classical waves passing through a double slit, similar to what you might have on a ripple tank experiment in school with water waves. If these are light waves, you can see them coming through the two slits, overlapping, interfering with each other, giving peaks and troughs. On the screen, where the waves are highest, where the amplitude is highest, that's where the light is most intense. What's striking is how this compares with the earlier experiment with individual photons passing through, because where the light is most intense, that is actually where most of the photons will concentrate on the screen, even though they're arriving as individual particles.
So could a classical wave equation be modified to calculate quantum probabilities? It was certainly a useful analogy, a good starting point. The end result of years of work by brilliant minds was this: the wave function. It's a mathematical solution of the famous Schrödinger equation that was first used to describe atomic electrons. It shared many mathematical features with classical waves, hence its name, the wave function, and many differences. The key one for us is that the amplitude of a classical wave carries one piece of information: its size. The bigger the amplitude, the more intense the wave. The quantum wave function, however, carries two pieces of information. Think of it as drawn by an arrow, which has both a length and direction. The length of the arrow is called the modulus of the wave function, and it's this value, the modulus, that turns the abstract maths of wave functions into a way of calculating probabilities.
Here's where Max Born comes in, one of the unsung heroes of quantum mechanics. He came up with this really clever hack. We now call it the Born rule. What he said was that the probability of finding a photon or any quantum particle, say in a particular position in space, is given by the square of the modulus of the wave function. And that gave the right answer for the probabilities.
Perhaps the most triumphant example of quantum wave functions is the way they perfectly predict the shape of electron clouds buzzing around atomic nuclei. But, and I can't stress this enough, this business of getting real probabilities from the wave function is simply a recipe, a mathematical technique which takes information about a quantum system and spits out probabilities. It doesn't provide a physical picture of what's going on. And that's the biggest problem with wave functions. However sophisticated your equipment, you never see them. For instance, this camera only registers single blips of dots. It can't record the wave function itself. It only shows us where, to use the technical jargon, it collapses. This puts the observer, the person making the measurement, into the heart of the story. It's quite bonkers. When I'm not looking at an electron, say, its wave function is a blur of many different possible states, implying, for instance, its position is smeared out in space. But whenever I look, it collapses into a single value. Somehow it seems like the act of looking is forcing the wave function to pick one value or another. Which brings us to hammer blow number 2.
The second sacred idea, and a rather profound one, that the founders of quantum mechanics were forced to abandon, or so it seemed, is something we call objective reality. The idea that reality itself doesn't exist until we measure it, until we look. There are several quotes here. So, example, there's a quote from Niels Bohr who says, "There is no quantum world. There's only an abstract quantum mechanical description. It's wrong to think that the task of physics is to find out how nature is. Physics concerns what we can say about nature." And then Werner Heisenberg says, "But the atoms or the elementary particles are not real. They form a world of potentialities or possibilities rather than one of things or facts." I'm going to go out on a limb, well, maybe not so much of a limb these days, and say I profoundly disagree with Bohr and Heisenberg here. In fact, I'm not alone. In recent years, certainly my generation of quantum physicists and those younger than me, I think have stepped outside of the shadow of the greats, the Bohrs and the Heisenbergs. And we're now arguing that actually there is an objective reality out there when we're not looking. This approach, which contains several different interpretations, is collectively called quantum realism. And this tells us that there is a world out there. It's not just brought into existence through measurement as those founders believed.
In the next episode, we take a deep dive into 3 leading quantum realism contenders: pilot wave theory, many worlds, and objective collapse. We'll be meeting 3 champions of each interpretation and seeing how they cope with perhaps the most devastating blow quantum mechanics deals classical physics: the problem of locality.